everyone. I'm Sachin. So today I'm going to talk about our system DeepSolarEye. So on the right side you can see two images. Both of these images have equal amount of soil, but they are producing different amount of power, which could be due to different factors like environment. So it becomes essential for us to identify, characterize, and localize the factors causing the loss in order to efficiently maintain the solar farms. So what we want to do is, like, given an RGB image of the solar panel, we want to predict the impact on the power level. We want to identify the area which is causing this loss, and we also want to identify the material type. To do this, we propose a four-step approach. We first learn the classification network. We then use the learned representation to create a candidate mask. Then we train a network to jointly do both classification and localization. And then we use the web images to train a small neural network to identify the dust type. So CNNs learn the representations in a top-down fashion by performing convolution and downsampling operations. With this simple network, we were able to attain an accuracy of 80%, which is good. But what they are learning, when we looked at the representations, we found that the spatial information is getting lost, which is pretty much important for a localization task when you want to do it in unsupervised fashion. In order to fix this, we propose a novel bidirectional input-aware fusion unit, which reinforces the input inside the network at different spatial levels to learn the dataset-specific representations. With this unit, the classification accuracy improved by 2%. But most importantly, our CNN was able to focus on the right areas. So basically, it helps in learning the dataset-specific features. So this second step in our pipeline is generating the candidate mask. So CNN learns features in a top-down fashion. We harness these learned representations in a bottom-up fashion to generate the candidate mask. In our network, we have two branches, which is called main branch and the auxiliary branch. We combine the feature map from these two branches using a multiplicative gating. Multiplicative gating basically suppresses the irrelevant features and helps in identifying the soiling area. With this simple approach, we were able to localize 42% of time correctly. We used this generated localization mask as our ground truth and trained an end-to-end network that basically predicts the impact level as well as the localization mask. With this end-to-end learning, our system attained a localization accuracy of 66%, which is like 24% more than the candidate mask. Now, our fourth step is identifying the material type. So we use the web images to identify the type of the soil. We trained a small neural network with those images. At the test time, we take the localization mask, extract the contours from the RGB images, and pass it through the WebNN to identify the soil type. I would like to emphasize that having WebNN as the separate entity adds a new flexibility to include new soiling types. So here are some results from our data set, and we could see that our network was able to do a good job in the localization task. But when we tested it on the images downloaded from the wild, from the internet, our network also performed well. Here, I would like to emphasize that our network was able to locate and classify the images, even on which we haven't trained our network, for example, snow, cracks. To summarize, we present a first CNN-based application for the domain of solar panels. We propose a four-stage methodology to completely bypass the human labeling for soiling localization. We found that the proposed BiDIAF unit has good generalization abilities, as you can see in the image on the right. Thank you.